Questions? Anything? Okay. Plans for this week, at least, to talk about to finish the clustering problem, one of our dynamic programming, maybe our last pure dynamic programming problem, and then talks about DAGs in graph and Dijkstra and multi and more revisit shortest path. Very briefly, it will take us maybe 40 minutes, where I want to show how, when we keep the principle of dynamic programming, all the variants of shortest path algorithms in graphs, positive weights, arbitrary weights, multi-commodity shortest path. We'll talk about it and why it is hard. We'll discuss this problem, and then we'll talk about some of the really, really useful results about set cover and sub-modularity, which is like how do we optimize functions that are, we'll wait with sub-modularity, and set cover will be our topic after a brief visit on graphs that will come right after that. But before all of it, let's finish with our clustering problem. So in the clustering problems that we discussed last meeting, I'm giving a set of points, uncolored of course, but very much ordered. I do care about the order. Presumably, if you'll miss the order here and the code runs properly, like you'll put 11 before. So I do care about the order. When you play with this app, make sure that the points appeared in the right order. You can move the points, but make sure that they appear in correct sorting order from left to right. A1, A2, A3, dot, 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 dot. Of course, they come without colors, and what we are asking is, let's break them into colors, like each color will represent an period, an era, an historic interval of time. We think about the X as a time, at which there is a simple behavior for all the points. Simple behavior is completely orthogonal to the problem. We want to say, if I can approximate the points with a simple function and with a small error, then I'll say they cluster well together. In this case, I'm using linear function, and I'm using a sum of square of distances, but that's completely arbitrary. We could have used any functions that we have in mind. And the main twist here is that we are not telling you exactly how many clusters we want in the solution. The way that we are controlling the number of clusters is by changing a penalty, so that every time that I start a new cluster, I have to pay this penalty. When I let you play with the app, the function over here just fits the best line, and it's a little calculator that you can change the penalty init will compute what is the total fitting error plus penalties that we are going to use. Okay, so any questions about the definition of the problem? So the problem is given our set of points sorted from left to right and giving the penalty, which is, once again, there is no correct and incorrect value of penalty. It's what the user decide upon, or more likely the user slowly change the value of R, the penalty, and see how the number of clusters in the optimal solution changes. And once the penalty is given, I can find for every cluster, I should decide where is the first cluster end, where the second cluster end, until ... the last cluster end, so that what am I minimizing? R times the penalty times the number of clusters, plus for every cluster, look at the best line that fits this cluster. I'll drop the notation L later on when I'll speak about the error. We'll use the notation error of ij, which would be a shorthand for error from pi plus 1, pi plus 2, ... of pj, which is a shorthand of error of L optimum of the set pi pj. So L star is the best line that fits these points, using, say, more or less a sum of squares of vertical errors. Okay, so that's our notation, error of ij. So if I didn't say anything about the algorithm, I just said that here is the notation that we are going to use. What is the total fitting price that we are paying is R per every beginning of the cluster plus the error for the cluster itself. And it's up to us to decide how many clusters, and it's up to us to decide where, in which indices h, I, and j start and stop. So how will this algorithm works? So there is a pre-processing step. Which is compute the error of ij for every I and j. You can do it easily in n squared time. How? We will go back to slides and we'll see that the error is just tells you find the best line for all the points start at pi and at pj. And I mentioned it last meeting, but let me re-emphasize. Once I said that pi and pj belongs to a cluster, then pi plus 1 all the way up to pj. All the points between pi and pj must belong to this cluster. We look at this formula. Just put all the points from pi to pj inside this formula, compute the sum of square of errors. That gives us the sum of square of distances. This gives us the error. And now if we are moving from I to I plus 1, or from j to j plus 1, let's move to j to error of I, j plus 1. Then you're just looking at these formulas, what is changing. The a and the b are changing because we are adding one term to each one of them. And they are essentially in constant time. We can move from the error of ij to the error of ij plus 1 So obviously we can do the whole pairs in order n square time. That's just a preprocessing. That's nothing to do with dynamic programming. And again, if I'll ask you to fit the points based on a different distance to a linear part, or fit them to a Gaussian, or fit them to a parabola, all fine. Wouldn't change one bit. That's the only part that the algorithm cares about it. Anyhow, I have the errors themselves. It doesn't mean that I'm going to use all of them, but at least I have them, all these values, in my deposit. The next part is that we will agree. We will agree because I say so, that for every cluster, it is the rightmost point that pays the penalty R. It will make sense in a moment. It's completely cryptic sentence at the moment. And as usual, C of I is the cost of the opt clustering of the, and we are using the prefix tweak. Using the prefix tweak, that is the opt clustering of the points P1 dot 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 Pi. Now, why does this problem smell like dynamic programming at the time? It will take a bit trickiness to get to the n square, but just to show you why it smells from dynamic programming. In all the problems that we saw, LCS, edit distance, triangulation of the polygon. Triangulation of the polygon I liked because it was the most visual example. I had my polygon. I thought, I checked the option that this is a chord of the polygon. That's part of the optimum solution. I don't know if it is, but assuming that it is part of the optimal solution of the polygon triangulation, then what I can solve the problem of anything to the left of this chord and the problem of anything to the right of this chord optimally, where they are completely separated from each other. Right? That's what suggests polynomiality, at least, because it's divide and conquer. Try and attempt to break it. It's not exactly divide and conquer, because in divide and conquer we usually split and solve each problem recursively and just merge them. Here we split, but also check other option of the splitting. So we are not sure that that's a correct split. But once we are testing one of the splits, then it just divide and conquer. Solve each sub-problem separately. The same happens with LCS, right? Once I matched one character to another character, whatever happens in my strings before this character and whatever happens after this character are separated and find the optimum solution to each problem independently. What you're doing in the right will not affect the optimality of what you're doing in the left and vice versa. Right? If you want to see it in contrast, the simplest problem, I guess, that doesn't satisfy such divide and conquer property would be try to solve a key-lock combination, right? You have multiple numbers to try, but Definitely you cannot say I'll just solve optimally the first 2 digits and then solve optimally the last 2 digits, and I have no idea how they match to each other. And we'll see other problems that we cannot really separate them later. What happened in the clustering? Let's say that I told you that this point, A10, is the last point of one of the cluster. A10 is the last point of one of the cluster. How would you solve the clustering of everything before it, and how would you solve the clustering of everything to the right of it? I don't know yet, but I'm absolutely sure that if it is the last point of one of the clusters, that is the next point will be the beginning of a new cluster, whatever is the optimum solution, it will consist of the optimum solution of the points after A10 plus the optimum solution of everything before A10. They don't influence each other. It wouldn't be exactly true if I would limit the number of clusters. If I would say I want exactly 5 clusters, that's why we are getting to the number of clusters somehow in the back door. We are controlling R, the penalty for cluster, and then we can see if the number of clusters that we are getting is too large or too small. But for each sub-problem, once I decided where to split it, the sub-problem before and the sub-problem after are completely separated. Cool? Okay, now to get to the desired running time, it will take a bit trickiness. Do you want to do it, actually? Does it look any better in this part? I'm not sure. No. Look, just a sec. Okay, finally, what's the algorithm? So, if Ci is the cost of the optimal clustering from P1 to Pi, then obviously C of 0 is 0. To cluster 0 points, I don't need to even pay my penalty. Okay, now, another common property of all the dynamic programming algorithm was that we are spending a lot of time discussing the algorithm, and finally the code is somehow anticlimactic. It's very short and concise and simple code after such a long discussion. Same here. So Ci0 and pi is used in the same way that we are using pi in Dijkstra and in the polygon triangulation. It somehow helps us to reconstruct what is exactly the solution. As usual, right now I'm computing the cost of the solution, and after I know the cost, I can backtrack. So, assuming that by now all the values of the optimum clustering, once again, optimum clustering consists of how many clusters and consists of what the boundaries of the clusters. And the cost is R times the number of clusters plus the errors that every cluster exhibits for the baseline fits this cluster only. So Ci, C1, C2, R of 2, Ci minus 1 contains the optimum cost for each one of these sub-problems. And now I'm in the problem of computing what is Ci. So what is my assumption? I look at Ci and I'll assume that Pi, every time that I'm adding a new point, this point is the rightmost point of a cluster. And if Pi is the rightmost point of one of these clusters, then it needs to pay a cost of R. We said the rightmost point of the cluster pays a penalty for the whole, its own cluster. Even if you have just one cluster, you still have to pay R. R is a constant penalty. The user decide what is R. It's a constant penalty that we are paying every time that we are using a new cluster. Remember, if R is 0, then we'll hit all the points with only one line. If R is very large, then probably we are taking every pair of points and fits a line through them. Pi is a rightmost point of this cluster. What am I asking with J? With J, I'll say where J will be the last point of the previous cluster. And I don't know what is this last, what is the previous point, what is the last point, the rightmost point. Pj will be the previous point of the, would be the rightmost point of the previous cluster. So let's think that I equals 10 right here. I equals 10, and J will play the role of A right here. That is, I is just A, the slider that I'm moving right here. And what's my option? If I'll take A to be 0, A, well, how to see, believe me, that's A, but think about it as I, anyhow. As J, sorry. Anyhow, last point of previous cluster. I is my, anything to the right of I, of A10, I don't know about it yet. I assume that A10 is the last point of the cluster that I'm building right now. And I'm wondering where is the left boundary of this cluster? Where could the left boundary be? If J is 0, then there is no previous cluster. If J is 1, then A is J. J is 1, then A1 would be the previous point of the only point of the previous cluster. And my current cluster, the one that contains A10, will start it right after AJ. So my current point will be starting at AJ. J will be, let's take general other value of J. Here, J equal 3. So in the previous cluster, clusters, maybe, I don't know that it's one cluster, but my current cluster will start at AJ plus 1 and will end at NI. Point after to the right of AI don't exist. So at the moment, I don't know about them. As far as I know, Pi is the last point that I need to consider. Okay, so I'm checking all the values from J goes to 0 up to I minus 1, which is exactly moving J over there. And as I'm moving J, notice this cluster is becoming smaller, and the previous cluster slash clusters becoming larger and larger. For every such value of j, what is the cost that I need to pay? I need to pay r, because we just said pi, the rightmost point, A10, is the one that needs to pay the penalty of r. It needs to pay the penalty of r. I'm assuming that all the points from j plus 1 to I lies in one cluster, so I'll measure the fitting error. I'll find the best line that match these points, the best line that matches these points. I'll measure the error, the vertical error, the vertical distance to each one of the points in the cluster. Look at this distance, this distance square, sum them up. This is what I'm capturing right here. Is this what CI needs to contain? Not exactly, because I also have points that lies from A0 all the way to AJ. Remember, AJ plus 1 is where my current cluster sits. So APJ is the last point in the previous clusters. What do I need to pay for them? Maybe I'll break them to one cluster, two clusters, three clusters, I have no idea. But I do know that CJ contains the optimum cost of everything up to and including PJ. So that's the cost of this part with the enormous, huge curly brackets. All the point of all the way from A1, all the points to AJ. And remember, if I don't have any such cluster, I don't have the previous cluster, my current cluster that contains A10 start at A1, and what do I need to add to it? I need to add Cj will be 0. But my current cluster starts at 0 plus 1, 1. And I pay 1 R, because it's just one cluster, plus the error line of fitting all these points, plus C of 0, which I initialize to 0. Now, what is the optimum value of j that I should pick? I'm not sure, but I know that it's smaller than I. So I'm just checking all the j's from 0 up to I minus 1. Which one should I take? As usual, the smallest one. Remember, I'm not committing right now that this will be part of the optimum clustering. But what am I committing? That if pi is the last point of all the data points, or later pi would be the rightmost point of one of the clusters, then ci will know the correct value of clustering all the points from p1 up to pi. Okay, so this part just computes the minimum of ci, making sure that ci is the smallest value. And to reconstruct it, what do I need to remember? What is pi of I? Just need to remember what is the index of j, that is, what is the point of the previous, what is the rightmost point of the previous cluster that I'll pick to use when I'm clustering the points from P1 to Pi plus 1. Okay, and in the next step, I'll just increase the point that I'm trying to cluster all together from A1 to from A10 to A11. Again, from A10 to A11. I don't know about A12, A13, A14. How should I cluster them? I'll try to check all the ways that I'll split the points between A1 and A10. And here in my GeoGebra, I just assume that 3 clusters at most, but of course, it could be that the optimum solution for the previous point will consist of multiple clusters. That's it. I think I have a set of points that represent the stock or the value of my stock. And I want to say here is a concise way to cluster them for any purpose. Now it's going down, now it's going up. What is the slope of going down? Now, looking at a single point by itself because of noise, it's not exactly of the line. I have no clue, just based on noise, to which cluster should it belong. I also don't know how many clusters are there, and that I cannot know. That's not something that the algorithm decides. But you are deciding how about a value of the penalty, and you see what is, for this value of a penalty for a cluster, that's the optimum number of clusters that you're getting. And the way to think about it is that we are thinking about all the values of R from 0 all the way to. Okay, so it's essentially to cluster the points into meaningful groups. But thanks, it's a good question. Okay, cool with everybody? Running time and square, not much to negotiate about it. I let you in the homework to explain exactly how do I find what are the points in each cluster. You're using the pi values for it, not hard. That's it. And altogether it's n squared because remember all these values errors was prepared in n squared ahead of time. Okay. And the n square space, why did I use the n square space, by the way? Where in the algorithm did I use the n square place? To represent the errors. Right. The errors was the only thing that takes some memory over here. Okay, so I thought that I try to talk about shortest path, various algorithm for shortest path as part of dynamic programming and see how ideas that we developed so far, how we are pushing them further. So I want to talk about topological sort. I assume that most of you know it, but just for completeness, let's go for it quite quickly. When topological sorting of the graph, and the term topological sorting, I think, is a great branding. I'm not sure what's topological about it, but let's not worry about it. I have all the vertices of a directed graph. I have all the vertices of a directed graph. I'll give a number to each one of them. Different number between 1 and n is a number of vertices. And I'll call this number the label of the vertex. And what I'll make sure is that if there is an edge, directed edge, the graph is directed, if there is a directed edge from u to v, then the label of u must be strictly smaller than the label of v. I don't have two vertices with the same label. It's strictly smaller than. So I have an edge from this vertex to this vertex, so the label of this guy must be smaller than the label of this guy. Okay, let's find the topological sort of this directed graph. You all know what I'm going to draw. Let's find the topological sort of this beautiful graph. Let's give 3 vertices. I need to give them labels, each one between 1 and 3. Let's try 2. An edge goes from here to here. The label of this guy must be larger, 3. Label of this guy might be larger, but I cannot do it because I just have 1 to 3. It will not work. So, and I could have started from 1 and run into the same issue. So, of course, I can find such topological sorting only if my directed graph doesn't have cycles, obviously. Now, if here is Kuhn algorithm, for finding if a graph is a DAG. If it is a DAG, then it will give you the topological order. And if it's not a DAG, you'll get an error message. You can use DFS. I think that it's more intuitive to use Kuhn. Here is my graph, A, B, C, D, E. And Kuhn algorithm runs in linear time. It will start with a set of edges, E prime, which is just the same set of edges. And I'll keep a counter that I'll use to give the label for every vertex. At the moment, the label of every vertex V is null, doesn't exist. And S is a set of all the nodes with no incoming edge. And it's going to be a dynamic set because I'm going to delete edges from the set. Okay. So E prime will start when E is just E, but I'm going to delete edges from E prime. Okay. So at the moment, S contains whom? A. Nobody has an edge going into A, and B. And the way that I like to think about, the way that I explain to myself what is this whole topological sorting business is think about all these nodes as processes that your operating system needs to perform. And this arrow implies that process E needs the output from D before you execute process E. The same, you need the output from C to execute E. What about A? A doesn't need anybody. You can start it at any moment. You don't need the input of it. What is the topological numbers? This order just tells you at which time in the schedule should I execute each process so that I'll never have to wait for somebody that didn't finish it. If I'll start from E, I'll have to stop E immediately because it needs the input from other processes before I'll wait for it. So the label is just the timing of all these nodes. Okay, so how do we run the algorithm? I'll pick from S some node. Let's say I'll pick A. I'll give A label, the label of the counter. Counter was 0, now it's 1, and that would be the label of A. And I remove every edge UV, that is, every edge that leaves U, I'll remove the edge UV from E. Remove UV from E prime, keep a copy of E, And a trick that I removed from the code is that for every vertex, I'll keep a counter that tells me how many edges are pointing to it. So when I remove an edge that leads to C, I'll decrement this counter. In degree, how many edges goes into C, this number will decrease. And when this number for a vertex reaches 0, it tells me there is no more edges pointing to it. Okay, so the edge from A to C was removed. S right now contains only B. So my next iteration will pick B, give it a value of 2, because I incremented the counter, and removed all the edges that are leaving B. So now S would consist of C and D, and so on. Right. C and D have no incoming edges. In E prime, I removed all the edges. Why? Because I assume that I already executed the processes, I generated the output from process A and process B. They're ready. You don't need to wait for them. So now you're ready to start either C or D. So let's give them value 4 and 3, and finally E will get 5. Okay, and it runs in linear time. So a few minor details that I'll let you enclose, but if you have not seen it before, but it runs in linear time, 1 per every edge. All assuming which data structure, by the way, to get linear time? Adjacency list. Every vertex needs to know who are its neighbors, who is this pointing to. So, okay, let's talk about path in graphs. You all know it, just to remind you. Every edge has a weight in my graph and the weight of a path. And the weight, and the weight of the path is just the sum of weights across this path. Yeah. Just sum up all the possible weights. That's just the weights, and I'll define the shortest path problem would be the path with the smallest weight, the cheapest weight, or a path with the cheapest weight, might not be unique. That is, and I'll denote it as delta from U to V, the path that starts at U and ends at V. And it is a minimum cost, the minimum weight of any such path. Sometimes I'll refer to it as a distance, and delta UV is infinity if there is no such path. Okay, our cut and paste lemma, we use the same lemma in all the dynamic programming algorithm. If I have the optimum path from S to T, here is the optimum path from S to T. Look at any portion of this, only any two vertices along this path, U and V. Ask yourself, what is the best path from U to V? Answer, take the big path that solves the big problem and just use the portion of the sub-problem that is relevant for you. And why do we call it cut and paste? Because had you have another better, cheaper way to go from U to V, then you could have used it also to go from S to T. You just go from S to U, take the dotted, and continue. Okay, quick notation. You have triangle inequality for the path. That is the distance from U to V, delta UV. And it's easy to get confused. We will have the value D in the algorithm. D and delta are not exactly the same. Delta is something that the graph decides about. It is not depending on any particular algorithm. Look at all the possible paths from U to V. Delta is the shortest one. D will be what the algorithm finds that might or might not be equal to delta. So triangle inequality, delta from U to V is smaller or equal than the distance from u to x plus the distance from x to v. Why is this true? Because when I think about delta from u to v, I think about all the possible paths in the world. All the possible paths that start from u and ends at v. What do I write over here? I ask for particular, I add a constraint that says I'm only willing to consider a path that goes from u via x to v. That is, it's path, not necessarily path that goes from u to v unconstrained, but it's a path that goes from u to v, but has to visit x along the way. You're adding more constraints, you need to pay for them, obviously. Okay, and notice that this triangle inequality has nothing to do with the exact weights of edges. Weight of edges might satisfy triangle inequality or might not, depending on your graph. It could be that this, the weight of these two edges is cheaper than the weight of this edge. That's fine. By the way, think about it, that makes sense about flight. Right? The more legs that we have in the flight, the cheaper it becomes, kind of. Or at least direct flight will tend to be more expensive. I'll use this analogy several times when we'll discuss multi-commodity. Negative cycle, any cycle that sums up to a negative value. And the problem with negative cycle are not that it caused a bug in the algorithm. It's the question of what is the shortest path from u to v makes no sense once I have a negative cycle. What is the shortest path from u to v? It will consist of go from u to this guy, do around the path. On this part, you have to pay for the path, so you want to minimize it, but along this part, you're being paid. So if you'll go over it again, you'll be being paid again. Go over it again, you'll be paid more and more and more. So the question of what is the distance from u to v doesn't make any sense. Of course, you can ask what is the shortest simple path that I don't visit any vertex more than once, but that's NP hard, and that's we'll not discuss this part. So just remember, if there is negative cycles, then just it doesn't make sense to ask what is the shortest path. The algorithm just needs to say there is negative cycle, so you'll ask stupid questions, you'll get stupid answers. And let's talk about Bellman-Ford algorithm. So Bellman-Ford algorithm says is a very, very robust scheme, paradigm that fits to many problems. And when it will implies to graphs with weights, it will make sense to ask it only for directed graph, because if I want to talk about edges that are negative. Some of the edges are positive, some of the edges are negative. Now, if I have two edges, if the graph is undirected and this edge costs 5, then what is the distance from A to B? Your path might go, then you pay -5, or you might go from A to B to A to B to A to B as many times as you want, and your cost will be cheaper and cheaper, so it doesn't make sense. So if I have negative edges, then at least let's talk about graph that is directed. Some of the edges are directed. Okay, and here is Bellman-Ford. Again, I assume that you have all been exposed to it, but even if not, for the sake of completeness, let's see what's happening. D of S, the distance from S to S, I'll assume that is 0. Is this a correct assumption? Maybe. Could it be that it's incorrect, that the distance from S to S is not 0? Yes, if there are negative cycles. If there are no negative cycles, then the shortest path from S to S is don't go anywhere. Every other vertex, dynamic programming, D of V is infinity. And now, what I'm going to do is to perform the relax operation. Let's meditate for a second about the relax operation. dov will be some estimation of the path to v. Dov will be some estimation of the cost of the path. S is the same all the time. It's a single source. Should have said it actually. S is a single source. Dov is my estimation of the path to v. What is a relaxed operation right now? Because I'm going to expand the relaxed operation to other scenarios. But here is S. It goes all the way to U. I'm meditating on the edge to V. And D of U will tell me what do I think is the shortest path. What at this moment do I think is the shortest path from S to U? What is the shortest path that I know about right now from U? And what does U tells V, given that there is an edge between them? That if I know about a path that reaches to me that costs $50, it will cost you $3 to go over this edge. So, hey, V, if the way to V will be go first to U and then use this edge, then the cost, as far as I know at the moment, to reach to V will be what? Would be the distance to U plus the cost of the edge from U to V. WUV is the cost of the edge. It's not the length of the path. It's the cost of the edge from U to V. That is, it will say you might get to U by paying $53. 50 plus the 3. And D of V might take you on this proposal, or it might say, hey, I already have a different path that reaches to me. V might say, there is a different path that I know about. Maybe it's not the shortest, but the cost of this path is only $40, and 40 is cheaper than 50 plus 3, so thanks, but no thanks. So I'll change D of V only if D of U plus WUV is smaller, D of plus WUV is smaller than D of V, and only then I perform the relax operation. And after, so the inner loop of Bellman-Ford, will do these operations for each and every edge. Which order? Completely arbitrary, because I don't know any better. I have no insight about at which order to perform it, so I'll just perform them in arbitrary order. The order that they appear in the file, the order that I read them from the input, all the edges. Now, what did we try? What was the invariant that we tried to keep in mind with respect to all the dynamic programming algorithm? When I looked at the LCS and I wanted to compute the value of this cell, I used the 3 cells preceding it, but I made sure that what they know is a final value. I needed to make sure that these cells are the final value. If I would have known that D of U knows the final value, the shortest path to U, it's not going to be updated, I would never bother of doing the relax operation once again for this particular edge. But I don't. So Bellman-Ford says, after you finish scanning all the edges, start and scan all the edges once again, because along the way, maybe the distance to U will decrease. And after you're doing, maybe the distance to U will decrease, and so on. Okay, and by the way, we'll prove that after n minus 1 iterations, d of u is a correct value, which means that if you are succeeding still to decrease its value, then there must be a negative cycle. That's these commands right here.
So we know where to stop if we found, for example, where to stop and we don't have to run all n minus 1 loop.
If you pass through all the edges and nothing change, then if you run through all the edges again, nothing will change again. So yes, you can definitely stop it the moment that, but as long as the graph, these values don't stabilize, then it's suspicious. Then maybe you can, maybe you cannot. You need some more information. But definitely, if I made this path, it's a question that I like to ask in the exam. I can start a flag here as to be false, and the moment that d of v is changing, then I'll set it to true. Help me to check if any of d of v has changed. Because if I pass through all the edges and nothing changed, no point of passing through all the edges once again and perform the relax operation. Okay, and then the running time of Bellman-Ford. Again, it's very robust. It will help. It will work for tons of weight values, tons of conditions. It will work for the multi-commodity shortest path that I'll define in a moment, and so on. So, the correctness of this algorithm, remember the delta from S to V is the length of the shortest path, property of the graph, nothing to do with the algorithm. And let's assume that the graph contains no negative value, then what could be d of v? D of v, if v is not s, then d of v starts to be infinity. But assuming that for some v, d of v is smaller than infinity, something gave it a real value. That's just a way to say it's a real value, it's not infinity. How come there is somebody that gave it a value? That's because some other node, v1, told v that it can be relaxed. It can decrease from infinity to somebody. Then how come then d of v1 cannot be infinity? Somebody gave v1 its value, which is not infinity, that must be v2. That similarly v3, and again in the lack of negative cycles, this must start at S. Check it out. So d of v will always be the length of a path from S to V. Maybe not the shortest one, but it's always a path. Now, delta of S of v, by definition, is the shortest path. So d of v always larger than delta. Okay? That would be for all the algorithm. Now, correctness, and I remind you that the same lemma that actually we used in the linear programming when we discussed a very strange way to find shortest path using linear programming. And that was a hint that I suggested. How do I prove that the result of the linear programming, trying to maximize the distances, modulo all the constraints, give you the shortest path? So, how do I prove that the algorithm is correct? I'll prove it by induction. And for this, I need to relabel the node. So here is my S that I'll call V0 at the moment, give it a new name. Nothing to do with the original V0. I change the names of every node. Here is my target, VK. And there is a shortest path. If no negative cycle, then there is a shortest path, and here is the shortest path. I just laid down the shortest path for you, and I give new names to all the vertices. V0 will be the first one, just a different name for S, V1, V2, V3, all the way. Okay? The relabeling was a confusing part. Now, after the relabeling, what do I know from Bellman-Ford? That at some point, I that Bellman-Ford made sure to go through each and every edge and relax it. D of V0 is 0. What do I know about D of V1? It cannot be larger than the weight from S to V1 once I relax this edge. Once Bellman-Ford got to this point, I'll consider the edge UV. At some point, it considered this edge. And what do I know about V1? First, what is the optimal path to V1? But if that's the optimal path to VK, and V1 is one of the nodes, then part of an optimal path is an optimal path. So the distance to V1 is just this edge. What is the weight of V1? Well, it cannot be larger than the length of the path. That was the first lemma. And because I made the relaxation, then the weight of it cannot be more than 0 plus the weight of this edge, implying V1 knows after one iteration, V1 knows what is the distance to it. That was after the first iteration through all the edges. Now, if V1 knows what is the distance to it, what is the shortest path to V2? Once again, it's part of an optimum is an optimum. The distance to V2 is just the cost of this edge plus the cost of this edge. If now at some point after V1 knows the distance to it, I'll access this edge, then the D of V2 cannot be larger than D of V1 plus W V1 V2, and cannot be smaller because of the first lemma, implying it's exactly the distance to it. After 2 iterations, after the 3 iteration, V3 knows the distance to it, and so on. Cool. Now, why is the number n minus 1 appeared? Well, because that's the longest simple path. Simple meaning no vertex appeared twice. That's the longest simple path that I can find. Cool with everybody? So that's why Bellman-Ford works. Okay. Now, here I'm really meditating on the relax operation. Why do I do the relaxing so many times? Again, because I'm not sure that D of U knows its correct value when I access it the first time. After I'll access it n times using this trick, I will know. But there are other tricks that will make sure that I'll access the vertices in the correct order. And when I'll access the edge UV, and perform the relaxation, D of U will know its correct value. There are a few tricks how I can guarantee it. How? If I run BFS or Dijkstra use its tricks with a heap that will make sure that once you access the edge UV, U knows what is the value to the distance to it. That's why you need to check every edge only once, comparing to the n minus 1 times in Bellman-Ford. The same goes for BFS, but the same goes for if my original graph is a DAG. Just make sure to access the vertices in the topological order. If my graph is a DAG, then one pass is enough. Let's think about it. If this is a DAG, and I'm not sure what is the label of each vertex, I'm not sure that the label of S is 0. Quite likely it's not. Let's say it's 17, but I am sure, but here is the shortest path. What I do is the shortest path. and there is an edge from S to A, so the label of A must be larger than 17, maybe 19. Definitely larger than 17 because there is an edge, and topological sort says if there is an edge from U to V, then label of S is smaller than label of A. Label of B, same reasons, must be larger than the label of A. Another edge from B to T. Again, that's the shortest path, but will be for every path will be larger than the length of B. Now, I use a topological order to tell me at which order to access the vertices. Then, at some point, I'll access S and give it a value which has value 0. And at this point, D of S is a correct value. It's 0. And in the lack of negative cycle, it will never be different than 0. It cannot be larger than. And it cannot, why it cannot be larger than? Because there is a path from S to itself of length 0. And it cannot be smaller than because it would mean negative cycle. So S knows the distance to it. And using all our principle of dynamic programming, we want to memorize values such that when I need this value, it's already computed. I don't want to call anything recursively at this point. I want to know that when I need a value, that is, when I need to know what is D of U, it's prepared for me in my memory. So if this is a path, then and I access the vertices in topological order, then I'll access A only after I access S. And S, by assumption, knows what is its value, and using the same lemma that we just showed, after I access S, A knows what is a distance to it. It will be S plus the weight of this distance. No matter what happens between accessing S and accessing V. Could be that I'll access many other vertices, but what's important, this happens only after this is done. And accessing B, that is B will play the role of U only after I'm done with V. So A knows what is the distance to it, then I'll access U. The numbers, by the way, is the labels that I got from the DAG. Maybe it was not clear. It's not the distances. These are the labels that I got, the topological order, to which time, which iteration, each one plays the rules of U. So when I need the value of A, I have it ready, which now implies that B knows its value, and then when I access B, B plays the rule of U. It knows its value and imposes it to T, and so on. But dynamic programming will work here. And actually in DAGs, there is lots and lots, which as an undergrad, I never saw how powerful DAGness implies. There are so many other problems that you can solve the moment that things happen in a DAG. Like geometrically, it's great if you think about gravity and think about anything that happens by height and influencer only from higher to lower. You got some DAGness. And it happens numerous times. And there is plenty of problems that you can solve in similar way in a DAG, and you cannot solve in other graphs. Like, if I'm trying to find what is the longest path, what is the longest path that starts at S? What does it say? It says, for example, that can I visit all the vertices of the graph with one path, which has a name. It's Hamiltonian path. It's NP. It's the classical NP-hard problem. In a DAG, it will work trivially. I just need to replace what do I need to replace if I want the longest path that starts from S? That if D of V is smaller than this number, then update it. So it's really useful, for example, if I have a set of points and I want to, you'll have it in the homework, I want to separate them into monotone paths. I want to decompose my data in various ways. It's really, really powerful, and it's kind of, and we don't have time to discuss the multi-commodity. I gave you one question about multi-commodity, I just didn't call you. it this way. Multi-commodity says that I'm looking at a graph where here is Netflix, here is me, and Netflix needs to rent fibers, rent channels from various providers. And every channel comes up with speed. The speed from U to V will tell you how much does it cost to send a kilo, how fast can you send a kilobyte from U to V. And it also comes with a cost per kilobyte. And so I have two parameters per every edge. And finding a path from Netflix to me, on one hand, this path needs to be fast. Especially think about Zoom, not about Netflix, then you cannot afford too much delays. On the other hand, we'll try to minimize it. But presumably the provider, the faster the service that they provide, the faster the link is, the more you're going to pay for it. So I have a set of speed and cost per every edge, and looking at a path, what do I look for one particular path P? I look at the total cost, and I look at the total delay. Total delay is how much did I delay on every edge along this path. Total cost is how much did I pay for this cost along this path. And now what is the question is that I'm trying to ask exactly? Like I'm trying to find one, but it's probably in contrast to the other. So a possible answer, a possible meaningful question here will be find fastest path with cost smaller or equal than $30. Giving the budget, what is the fastest path? Or giving the target speed, what is the cheapest path? But you have to decide what is your question exactly. In general, that's NP hard. It's kind of interesting. You have exponentially many different paths, and you're trying to find exactly one of them. You can have exponentially many different paths, and each one have different cost and different price. Not too hard to show it. In certain cases, you can solve it much more reasonably, but all the time you can either approximate it or solve it exactly. Like in the homework, I ask you to solve this question, but here the cost of every edge was 1, which simplified things dramatically. If the cost of every edge is 1, and I'm trying to ask for every number of edges, how many? And the big hint is, go back to the relax operation, go back to Bellman-Ford. But now what I store in D of V and D of U is not a single value, but I'll store the D of V and D of U a certain set of values. For example, what is the shortest path that contains 1 hop? What is the shortest path? Shortest path weight-wise that contains 1 edge. What's the shortest path that contains 2 edges? What's the shortest path that contains 3 edges? So you're getting a value of at most n numbers for V. And the same, you're getting n values for U. Again, shortest path, sum of weights, with 1 edge. Shortest path with 2 edges, 3 edges. There are n possible values. And now when you're considering the edge WUV, it will help you ask how do I do the relax operation for any of the values that I keep in these arrays. Not hard. And if and Bellman-Ford just works very nice for it, and it's essentially very much used for approximating or finding exact multi-commodity, that's called multi-commodity or two-commodity, multi-commodity shortest path, which is again type of problems that are much, much more common than you'll find. There are many more practical questions that have more than one parameter. Like you want to go for the shortest path from S to T, but you also want that it will be energy efficient and there will not be traffic, and there is extremely practical question. Good. Thank you.